Welcome to my channel Mydhili SK. In this session, I am going to start with the subject EC 3491 Communication Systems, which is for a 4th semester secondary ECE students. So, I am Mydhili SK, working as professor in Department of ECE, KGSL Institute of Technology. To start with the syllabus, Unit 1, it is about amplitude modulation. So before going into the amplitude modulation techniques, we have to start with the review of signals and systems and followed by the importance of time and frequency domain representation of the signals. And then it starts with the modulation, types of modulation techniques, and basically about the unit amplitude modulation. So in amplitude modulation, different types of amplitude modulation techniques are there. So those amplitude modulations DSP, SSB, VSB are explained, and their generation is also explained. You could see here SSB generation. Actually, though it is not specified, every generation and deduction techniques will be explained. And then here it also explains about the angle modulation, which is about the FM and PM signals. Then about the Hilbert transform, pre-envelope and complex envelope AM signals. Then finally it ends up with super heterodyne receiver. So at the outset, at the end of this course outcome for unit 1, you will be able to gain knowledge in amplitude modulation techniques, which falls under K3 level, that is apply level. So today's topic will start with review of signals and systems, time and frequency domain representation of the signals. This is actually taught in the last semester itself. So what is a signal? Signal is nothing but a representation of physical quantity, sound, temperature, intensity, pressure, etc., which varies with respect to time or space, or independent or any dependent variable. So the variable can be which is dependent or independent factor, or simply it can be defined as a single valued function which carries information by means of its amplitude, frequency and phase. So for our part, we are going to concentrate only with this second definition now. But previously, when the basic signal is represented, you should identify, and in terms of real world scenarios, you should remember that signal can be of any form. So actually whatever I am speaking now is an audio format, that is a sound signal. So that is an example of a signal. So here are some of the examples you can relate. The voice signal, what I am speaking now, video signal when you watch movies, and signals on telephone wires. Nowadays we don't talk about telephone, we can say about the cell phones or mobile phones. So how the signal is represented mathematically. The signal can be represented mathematically in terms of sinusoidal format or cosine format. So sinusoidal format means x of t is nothing but a sine omega t plus phi. So this is nothing but a represents the peak amplitude and f represents here the angular, that is omega here the angular frequency, and in terms of frequency it is 2 pi ft. So frequency is inversely proportional to time, and what is this phi is nothing but the phase change. Now showing it graphically, this is how the signal representation of a sinusoidal signal is. So you could remember or recall the signal representation in a sinusoidal format. This is one cycle of waveform which travels along the time axis, and this equation x of t represents by means of the amplitude along with the signal contained in the format or which format the signal is present. So signal with different phases, amplitude and frequencies are explained now. Now talking about phase, phase is nothing but with respect to angle. So here this is the basic signal which is starting, whereas here you could see here the signal is starting from 1. So here we can say there is a minute or phase shift which is a 90-degree phase shift has happened. If it is a 180-degree phase shift, we can say here instead of this, you could see the signal is starting from 0. So this is what the signal representation in terms of phase. When we are talking about the signal representation with respect to phase changes, amplitude changes, you could see here from a basic sinusoidal signal. Example, the representation of signal which is changed by the amplitude level is shown here. So now this is the peak amplitude level. You could see the difference between this diagram and this diagram, where the peak amplitude level is high here, whereas here it is low. So whenever it is changes with respect to amplitude level, that is y-axis level, here the height of the signal is varied. So that is called the amplitude changes. Next, talking about the frequency, you could see here, as I said, time is inversely proportional to frequency and vice versa. Actually, we are talking about a signal or sinusoidal signal in only in terms of time domain representation, that is in t scale. So we could see here a sinusoidal signal compared to the signal, this is very close enough. So for one particular sinusoidal signal, the contained frequency when it is converted, this time is very large, whereas this time is very small. So when it is inversely proportional, this will be very small in case of frequency, whereas this case it will be frequency will be high. So this is how we can say in terms of frequency it changes. So classification of signals, basically we know it is divided in terms of many types. Basically in terms of one dimensional signal, when the signal is varied with respect to one variable, it is called as a one variable signal, or it is a single valued varied function. So simply we can say a sinusoidal signal, which is our representation which is varied along the time axis, is an example. So example includes an audio signal, biomedical signal, temperature signal, so which is dependent only on the factor along time axis. So these are some of the examples. Now coming to the two-dimensional signals, as I said, relate only with the two-dimensional data. So it is dependent on variable with respect to two-dimensional changes. So two valued function or two variables will be represented for using the changes. So instead of only along time scale, here and y-axis scale is also considered. That is x and y coordinates are represented. You could see here. Next, about the three-dimensional. So along with x and y, if you are adding another coordinate or a point or a variable, then it is called, the signal is three-dimensional signal. Example, along spatial coordinates x, y and time is also included. So these all are very useful in case of image processing techniques. So in forthcoming classes or semesters, you will be studying about all these applications and you can relate this signal representation. So classification of signals generally based on the types with respect to nature of the signal is continuous and time domain, sorry, discrete time signals. So continuous time signal is nothing but which varies with respect to which continuously varies with respect to the time. Whereas in case of a discrete time signal, it is discrete in set of values with respect to time. So it is not dependent on the time. So here it is dependent on the time. So in between you could see it a digital signal which contains only two values in terms of zeros and ones. That's why you study the subject digital systems. So when talking about discrete time signals, as I said, it is represented in terms of samples. So continuously, if a signal is drawn, so he could relate here to remember continuous time signals, you are not taking the pen and you are drawing it continuously till the end. So this is a continuous time signals. So relate with DT signals, whereas here it is represented in terms of samples only. So you need to take the hand and you will be drawing or representing the signal where the samples are present along the n axis. That is here t, instead of t we are representing it as n. Here they have shown as k. So variables may differ but the meaning is same. So discrete time representation is very important when talking about the future, that is digital signal processes, etc. So it is always represented in terms of n variables. So variable n is used to represent, that is number of samples here is n. So how this graphically is represented is very important. So as I said, it is represented with a knob where the signal value is represented with respect to the presentation of the signal. So tabular representation, maybe we use it rarely, but in a signal representation this is very important. And when coming about the functional representation, the same equation or any signal can be represented in terms of equation. So x of n here, what they have written here is, if you are drawing this signal, it will be x of n value for n, and n is equal to 1 and 3 here is 1. So already these signals we have drawn here. Actually I have shown this in our last class, that is in signals representation itself. If you do remember, if it is x of n and this value here, it is 0, 1, 2, 3, 4. The maximum n value representation here is 3. So this is just a positive value n. So maximum height the signal going to take here is 4. So in x-axis you could take it as 2 and 4. So here, what is the value for n equal to 0? They haven't given, but for n is equal to 1, the value here is 1. So how we are going to represent for 1 here is, simply represent here, the value here is, for 1 it is 1, and for 3 is also 1. Sorry, it is not marked as 0. You should mark here for 1 only. There is no 0 value. So for 3 also it is 1. For n is equal to 2, here it is 4. So here it is 4. So this is how, and 0 elsewhere. So for remaining all the values you should plot 0. So this is the actual representation for the equation format given. So mathematically a signal can be represented in terms of equation, that is summation or x of n. So here x of n for x of t ranging for nth sample with respect to time, or simply x of n into t. So what is a system? So system is nothing but, so when talk about signals, we talked about the signal representation in terms of audio format or video format, text format, etc. Now in terms of systems, signal is an input quantity, means then we need that signal to be processed in some device. So this is a device or combination of devices which operates on the inputs whatever is given. The input here is the signals, and it produces the corresponding output. So input to a system is called as an excitation. So in case it is different for each of the system representation hereafter, whatever you look into the course. So now actually we have seen about the system. What is a system here is, the system consists of an input and it produces an output. This is the basic understanding you must know. So here the subject we are going to study here is communication system. So what does communication system does? It takes the input value, modulate it and produces the output simply. So when talking about communication system, here falls with transmitter and receiver. So all these transmitter and receiver comprises with the system. So this is the relation I can give with system, signals and systems, and why we are going for communication systems. So actually in signals and systems you studied about the system, that is input is referred here as excitation and output is referred as responses when you go for the discrete type of setups. So for more or one or more inputs, the system can have one or more outputs. So as I said, the example can be a communication system itself, right? As I said, this will be the best example I can give you now, right? Okay. So system classification, this is, I hope you do remember, and which is very important when considering system here is the linear time invariant system. So we have been studying about the linear time invariant system, which obeys the properties of both the superposition principle and additive property. So these are all, hope you recall. If you want, you can watch these problems in my channel. Hope you do remember, which depends on the present input state and produces an output, how it is differing. So this is what I have conveyed and represented in terms of signals. So this is actually I made the PPT with respect to the last signals and systems what I have taught in the class, and this is just for a recall. Again I have giving in terms of classification. Hope you remember this: deterministic signals, random signals, periodic signals, aperiodic, even odd, energy power signals, etc. So now we will relate how this importance of the signals in terms of signal operation is considered. So when talking about the signal operation, these four operations are very important. That is time shifting with respect to x of t minus t naught, time scaling with respect to along the time axis only. So here the representation of a into the time domain scale. Time reversal means x of t is represented as minus t, so it is reversed. Amplitude scaling means the signal is actually there, whereas the amplitude here is multiplied. So these four are very important operations. So system, as we have seen, just recalled the same. Now coming to the importance here. Impulse response and convolutions are very important. These terminologies are used in further classes also. Impulse response means the response which is always 1 for a 0 state, right? So it is represented as a delta input, that is del of t is equal to 1 for n equal to 0. Otherwise it is equivalent to del of t is equal to 1 at n equal to 0, and remaining cases it is all 0. Yes, the same. Next, convolution is very important. When we are talking about convolution, you should remember and recall my class how the convolution is explained, right? So convolution is explained in terms of two representations. One is for CT and another in for DT. So when talking about CT signals, this integration parts plays a major role, because we know continuously we are drawing a signal, so this signal will not be captured. So when we integrate it with respect to time, it can be simplified. So integration plays a major role in terms of continuous, whereas for discrete, as I said, the signal is represented in terms of samples, which is not dependent on the time. So here you could see here there may be a signal for 0. For 1 it cannot, the signal will not be available, that is 0. For 1 again it is 2 means, for 3 again it is 0, etc. It going on like so. Here the signal is not needed to be added. So finally when we want to convolve a function with respect to two signals, we will go for adding of these signals. So summation plays a major role with respect to dt. Hope you remember all the sums we have worked out for the same. Yes. Next is a Fourier analysis. So Fourier analysis plays a major role when we are talking about the time domain representation x of t to x of f. X of f is nothing but t is a time domain representation, f is the frequency domain representation. So for a Fourier series, we are representing a periodic signals means with respect to summation part. Here you could see here Fourier series for representation in terms of sum of a sinusoidal representation is given here in terms of exponential representation. Sometimes it can be used with trigonometric series also. Next, Fourier transformation, as I said, do remember about the conversion factor with respect to converting time domain to frequency domain representation, and basic equations is given. And convolution sum, as I have explained earlier. So what is the important property when considering about Fourier series and Fourier transform is linearity, time shifting, frequency shifting, and convolution theorem. All these properties we have seen in the important functionality what with respect to x of t, time reversal x of minus t, and scaling function x of at, and amplitude scaling with respect to x of at, etc. So in terms of frequency shifting means with respect to x of t, here x of f will be shifted, that is x of minus f or anything. So with respect to frequency, if there is shifting functionality. Convolution, as I said, for continuous time it is integral, for difference discrete time it is summation, right? Now talking about sampling. So sampling plays a major role when we are talking about a communication system. So after a conversion factor, x of t signal is converted to x of f. So why this is very important? Because conversion from time domain to frequency domain is important in the communication systems, where uh, the introduction part I will explain. For a transmitter end to a receiver end, that is from a source to destination, how the signal is transmitted. So from one place, if I am having, if I am here in a long distance, that kind of modulation comes into the picture. That is, modulation comes into the picture when we are talking about the non-line of sight communication, where devices comes into picture, that is the transmitter and receiver part. So when the transmitter and receiver part comes, so in between there is a vacant place that is called as channel. So the channel is nothing but the medium through which the communication is held. So now, if we are having an offline class, I will be directly speaking to you, and you will be hearing my voice. That is at the example. In a communication system, I am the transmitter and you are all the receiver. If it is an offline class, the medium will be the air. So through the air, whatever I am speaking, that is a human audible range is 20 hertz to 20 kilohertz. So here I am audible to you. 20 hertz to 20 kilohertz, I am audible to you. But now it is an online class, means I need to use some device, and we need to convert it. Or if it is a live streaming session, we need to go for a streaming signal, and there requires a modulation part, and there requires a channel which is a wireless channel which uses the electromagnetic waves. These electromagnetic waves travels only in the air, and that too this electromagnetic signals will carry with a high frequency range. So this is a low frequency range, so it doesn't need any medium to transmit. But when talking about a distance communication, their frequency whatever we are using will be high in nature, so we need a uh, devices which will enable us to take the signals. So here, hence whatever I am talking here, an analog signal which is represented in time domain representation need to be converted in the format which will be carried in the spectrum, that is channel electromagnetic waves. So we, that is only in the format of frequency domain. So the frequency domain plays a major role, that is conversion factor plays a major role. So when we are talking about the frequency domain representations, or x of n sequences, sampling plays a major role. So when analog signal is converted into a digital signal, this sampling plays a major role. So what is an analog signal conversion to digital signal here is, so example, if this is the analog signal, and here I am going to sample this at a duration of t samples. So how this sampled output will be is, example, yeah, this. So if you merge this signal, it will be sampled at a duration, and you could see the same signal can be represented simply like this. That is, simply sampling process is nothing but CT format to DT format, right? So CT format is this and DT format is this. By means of this sampling duration, we are going to convert it. So what is the condition under which this sampling will be helpful here is, Fs is greater than or equal to twice that of the maximum modulating or message signal frequency. The sampling frequency should be following this condition, right? So why this is condition is necessary means, in order to avoid the aliasing. Aliasing means overlapping of the signals. To avoid overlapping of the signals, this rule is to be followed. Then system analysis using transformation. As I said, transformation plays a major role. So the earlier explanation about x of t to x of f is actually here, where the signals and systems covered in the last semester is explained with respect to transformation, Fourier transformation, Laplace transformation and Z transformation. So Fourier transformation basically gives about the continuous times. Both the Laplace and Fourier is about the continuous time. Fourier with periodic, but here Laplace can go for aperiodic also, right? So basically it is nothing but converting a time domain signal to a frequency domain signal. In terms of Fourier, in terms of Laplace, it is in terms of S domain. S domain is also a representation of power spectral density function with respect to frequency. When talking about the samples, so here Laplace transformation is concentrated only with continuous time systems, whereas Z transformation is only concentrated with discrete time systems. So discrete time systems conversion factor with respect to Z transformation. So next important parameter you need to know about is the noise. So actually this I have explained in the class with a live demo by switching off the fans in the class. So the same example, I am the transmitter, you are all the receiver. So when I am talking to the class, when I am discussing or delivering a lecture, my signal, that is whatever I am speaking is the signal, my signal quality will be high when the noise around the class is quiet, right? So by switching off the fan, I have showed a light demo in the class. If you could recall, please do recall and see. When the fan is off, the signal level was high, my voice level was high, but the noise level made by fan is reduced. It is not made to zero. That is, generally the environmental noise comes into the picture now. So noise, what is the ultimate outcome I am trying to explain here is, noise in the environment cannot be made to zero, but it can be reduced. When the fan is switched off, you are able to hear the environmental noise, example a bike sound or a next class lecturing session sound or a student passing by sound. Everything will be heard. So signal to noise ratio is very important. So it is nothing but explained with respect to the ratio of signal power to the noise power. So it plays a major role in analysis of a signal in terms of output, signal power to the noise power. So when the signal power is high, the monotonic curve will be high and the efficiency of the transmission will be very good. That is what the output we can give. So this noise in communication system plays a major role in research, where this will be helpful to say how a communication system is good or bad. So this is very important and we'll be seeing about this with respect to additive white Gaussian noise. So this is explained by a scientist called Gaussian. So it is named after him as additive white Gaussian noise. So now coming about the importance of time and frequency domain conversion. Hope you could recall the factors why the time and frequency domain conversion is very important in signal processing engineering and various scientific field. So now we could see, or when talking about a communication system itself, this x of t to x of f plays a major role. So this, it allows us to analyze, manipulate the signal level depending on the specific application. The application may be different. Now in terms of communication, it is nothing but a transmission of the signal. So when it is depending on the application level, it differs. So this can be achieved only by transformations like Fourier and Laplace. All these we have seen now. Why it is very important, why the signal in terms of filtering is very important. So as I said, noise reduction can be done, and By means of filtering, we can avoid the unwanted noises. So, in case of any application with respect to systems, we can go for this filtering effect and noise reduction techniques. And in a case of communication systems, we can say in frequency domain, example like AM, FM radio. So the effective transmission and bandwidth utilization all depends on this conversion factor. And the demodulation is a part which converts back to the time domain signal itself. And in also it is applied in system design and stability. So just recall about the control system paper you have studied, which is used in analyzing systems in the frequency domain concept with respect to Bode plot or Nyquist plot. So there you will be studying in terms of frequency domain representation. Why you go for control system or importance of control system is it helps you to determine the stability of any system and its performance measures. So example, designing a feedback often system in terms of autopilot control system in an aircraft is an example I can relate with the control system subject. Right. In terms of data compression, if it is a CSE domain, frequency domain techniques plays a major role with respect to many signal representation characteristics. So where the image and video compression algorithms are very important. So example, if you are considering mobile phones, you are having your mobile phones, you are clicking pictures daily. If you are saving it in a memory card, once the memory card is filled, you need to delete it. So instead of deleting it, if you compress the same image to the size level which is very reduced level, then it will, the space occupied will be more. So instead of occupying one image with this much of size, that is example 3 Mbps etc., if it is saved in just zero point 0.5 Mbps, then you could see here the same picture without losing its reduction in quality, just spare saving the space. That is called as data compression. That is also where we can go for time and frequency domain conversion. So mathematical transformations already we have seen in terms of x of t with respect to x of f. Hope you recall these equations with respect to x of t and x of f. So what is the advantage of frequency domain analysis is, as I said, it simplifies the mathematical operations, identification and manipulation of specific signal components, and better for system designing and optimization, and it enables noise reduction by filtering. So what are the key takeaways of today's class with respect to signals and systems for a communication system is, so communication system relies on this frequency domain analysis with respect to the input which processes on the signals and transmission happens. So communication relies heavily on these transformations for modulation techniques where x of t will be converted to x of f, and also it involves the filtering and signal reconstruction techniques at the receiver end. Then frequency domain representation simplifies the complex modulations and demodulation process. In case of time domain and frequency domain conversions, for all the above topics, whatever we have discussed with respect to communication, this plays a major role, or it is a foundation for a modern communication system which enables efficient signal processing, modulation, noise reduction, data transmission across various channels. So conclusion, we have seen today about the signal. What is a signal is nothing but behavior or attributes are dependent on the some physical quantity. It is simply known as the input. What is a system is nothing but which processes on the given signal input. So the signal can be analyzed in terms of time as well as in frequency domains. And system processes on the input given, that is signals, and their behavior can be described using in terms of impulse response and in terms of convolution. So when talking about conversion factor, time and frequency domain plays a major role, which is an important tool in understanding, analyzing, and processing of a signal. So, this time domain gives us a view on how the signal behaves over the time, whereas the frequency domain reveals on the spectral component of a signal. Spectral component is nothing but the shape of the signal which is contained with respect to the signal, that is called as a spectral component. Both perspectives complement with each other, that is time domain and frequency domain complement with each other and are crucial in many fields like telecommunication, audio engineering, image processing, and control systems, which plays a major role in our day-to-day life. Hope you understood today's session. Thanks for understanding. Thank you.